In this example, I want to show how to calculate the electric field at some location in space produced by multiple point charges. In particular, in this example, let's say we have charges Q1 and Q2 separated by some distance A along the y-axis. And let's say the location where we want to know the electric field is at this location, is this X. We'll call that the field point. Let's say the field point is located a distance B along the x-axis from charge 2. All right, so here's our plan of attack. We find the electric field contribution at the field point due to Q2. We find the electric field vector contribution at the field point due to Q1. We'll call those E2 and E1 vectors respectively. The electric field overall at the field point will just be the vector sum of those contributions from the individual charges. All right, so let's get started. We need to apply the formula for the electric field due to a point charge. So this is the electric field produced by some charge Q. In this formula, K is the Coulomb constant. R is the magnitude of the separation vector from charge Q to whatever field point we're interested in. R hat is the unit separation vector pointing from charge Q to the field point. So let's apply this to the case of charge 2 producing an electric field at this field point. So we'll draw in our separation vector and unit vector. So pointing from charge Q2 to the field point, we have some separation vector I'll call R2 vector. We've got a unit separation vector R2 hat. Okay, so we can plug all this stuff in to this formula to get the electric field vector E2 produced by Q2 at the field point. So we have K, Q2 in place of Q, R sub 2 magnitude in place of R magnitude, and R2 hat unit vector in place of this general unit vector. Okay, we can go further. We can put this in terms of the parameters specifically in the problem. In particular, we know that the separation vector from Q2 to the field point has magnitude B. And we know that this separation unit vector direction, well, that's just in the x hat direction. So this unit vector is really x hat in our particular problem right here. So we can make those substitutions, put them here, and I'll do that now. Okay, we can also represent what that means on this diagram. Now, we got to keep in mind that charge Q2 could be positive or it could be negative, and that'll then influence the direction of the electric field here. K is constant, B squared obviously is constant. So if charge 2 is positive, this vector will point in the direction of the x hat unit vector. If charge 2 is negative, then this vector will point opposite the direction of the x hat unit vector. So for the purpose of just representing things in this diagram, let's pretend for now that charge 2 is positive. So the contribution E2 vector will be this direction here. And I'll put a little asterisk next to it just to remind ourselves that that's only in the case where charge 2 is positive. If charge 2 was negative, the electric field contribution E2 vector at this field point would be to the left instead of to the right. So we can do the same thing for charge 1. So we can apply this formula for the electric field vector at the field point due to charge 1. So we need to write in a separation vector from charge 1 to the field point. I'll call that separation vector R1 vector. We can put in a separation unit vector that's in that same direction. And now we can apply this formula to find the electric field vector contribution at the field point due to charge 1. Now, before we do that, there's a simplification we can do that's useful in some cases. We can write the R hat unit vector in terms of the separation vector divided by its magnitude and plug that in here. And then we can get this. So we got to be careful. In this expression, we've got the separation unit vector, and we've got an r squared on the bottom. In this expression, we have the separation vector, and we have an r cubed on the bottom. They're the same formula, just represented two different ways. All right, so here we go. For the electric field contribution at the field point due to charge 1, I got K Q1 over R sub 1 squared R1 hat, or I can write that as K Q1 over R sub 1 cubed R1 vector. So now we need to do a few things to plug in. First, let's note that R1, that's the magnitude of the separation vector from Q1 to the field point. So if this length is A and this length is B, and we've got a right angle here, the length from here to here, that is the magnitude of the separation vector from Q1 to the field point, will be the square root of A squared plus B squared, which I can write this way. So ultimately I'll need to plug that in. I'll need to take this thing, that's R sub 1, I'll need to cube it and put it into this. To find R1 vector, well, R1 vector is going to be A times Y hat plus B times X hat. All right, so we'll take that information and plug that in here as well and rewrite this expression in terms specifically of the parameters in our problem. We do that now. We can represent the direction of E1 on our diagram. Let's revert to this expression to do that. So if Q1 is positive, then E1 will point in the direction of R1 hat unit vector, which is in that direction. So if Q1 is positive, the electric field produced by Q1 here would be this way. On the other hand, if Q1 is negative, the electric field at this location produced by Q1 would be this way. So let's provisionally assume that Q1 is positive. We'll write in that electric field vector contribution here. Call it E1 vector. I'll put a little asterisk by it to indicate that the direction of this, like the direction of this, is only correct assuming that these two charges are positive. Now, having said that, I want to emphasize that our analytical expressions, the way we've done them out in full-blown vector notation, are going to be correct regardless of the signs of the charges of Q1 and Q2. All right, so having found the electric field 1, electric field 2, we could find the net electric field at this location just by summing up these two vectors. That is, algebraically, we can put this and this, and that'll be our total electric field. I'll write that down in a moment. But first, I'm going to note that we can also do this graphically. So if this is E2 and that's E1, we can do graphical vector addition by completing the parallelogram, which is equivalent to taking the tail of E1 and putting it to the tip of E2. The net electric field then would be right like that. And this would indicate its magnitude and direction of the net electric field. So that's the graphical representation of the net electric field at this location due to these charges. A couple notes. First, the relative sizes of these arrows depend on many factors. They depend on these actual distances, and they depend on the relative amounts of charge here. Note that the electric field, the more charge you have, the stronger the electric field contribution to a particular, at a particular point, from a particular point charge. However, the further you are away, the weaker the contribution. So if these two charges had about the same amount of charge, then this arrow should in fact be shorter than this one. However, this arrow could be longer if you had a boatload more charge here. So we've just made some guesses. We'll assume if these are correct, this would give the correct electric field vector graphically. However, our analytical expressions are correct regardless of the signs of the charges or the sizes of A and B. And so we can take this, add it to this, and get the net electric field right here as follows. And this is our symbolic expression for the net electric field at the field point produced by charges Q1 and Q2. There's lots of different ways we could write this. I've pulled out the Coulomb constant K. Normally you group the X component stuff together and the Y component stuff together. So this is one of many defensible ways to represent our result. One final important point. We've used the fact that the electric field vector at this location is the vector sum of the contributions from this charge and this charge. This is a vector summation. This vector summation also, of course, holds for the components, but it doesn't hold for the magnitudes. All right? The magnitude of this vector plus the magnitude of this vector will not give you the magnitude of this vector. This is a vector addition, not a magnitude addition. Thank you.